I mean, the remaining 3 hours. So what I would like to do now is finish the Cutset bound and then do the partial decode forward strategy. Maybe I'll get started on Quantize Forward, and then tomorrow I should finish the relay channel section, and I might have a little bit of time to talk about some extensions of that to networks. But we're effectively, you know, going to stick to the relaying as a whole in terms of the topic. So what I wanted to do is prove this Cutset bound formally for the relay channel. So that's what we want to prove. You'll see there's absolutely nothing strange about the proof. It's actually quite straightforward, which is why it's also so generally applicable. You don't need any special tricks to prove this. So if we think of how we're starting, as usual, I start with for reliable communications. Maybe let me run, I could once write it out formally. So Fano's inequality gives you the following, right? That W hat. And then if you're looking at bit error probability, you would have down here H2PB, average bit error probability, right? And then if bit error probability goes to 0, this just becomes 1, right? Or if we're looking at block error probability, I have to think of what the bound looks like now, but I think it's 1 minus PE plus H2 of PE. That's the fully valid bound on block error probability. Again, when I write reliable communications, I mean P goes to 0, this goes to 0, and this goes to 1, and we just get mutual information. So that's why I always like to start with the end-to-end mutual information first, right? The message, where to its estimate. Okay, but formally, some people wouldn't be happy with this bound because, you know, actually I should adjust it slightly. If you want to be very pedantic, then you will reject the paper because this inequality is incorrect, right? Okay, well, whatever. Fine, we start here. Now I'm being pedantic. So. This, through the data processing inequality, this is less than y3n, right? So that's could be our starting point as well. So let's just work with that. So we'll work with that without much further ado because this already looks close to this. In fact, it looks so close that it shouldn't really play much role. So if I say, so I can write this as h of y3n minus h of y3n given w, of course, and this is just h of y3i minus 1. All right, that's just all that's with equality, those two. This here, of course, so this is where I'm going to want to get my y3 from. And here, I can just stuff in here, right? Greater than or equal to h of y3i. And in particular, all I'm going to stuff in is x1i and x2i. And then you can show that you may as well drop those because this is just a noisy version of that, right? And this is just past and present random variables. If there were future random variables here, then potentially the future ones might influence the, you know, the choice of future values. So you have to be sometimes careful, but whenever you just have stuff in the past, we can just drop it. There's a markup chain. I mean, I could give you an example, like especially when you have feedback channels, you have to be a little careful sometimes. But this always works. But if you have stuff in the future, sometimes you can't drop stuff. So, but this here is actually equal to h of y3i given x1i, x2i. Okay. And then we're almost done, right? So now we have this is less than I x1, I x2i, 1i. 2i, y3i, and you see that we have our form. The only thing we have to do yet is single letterize this. So we just use our usual trick that we write we define a time sharing random variable, we multiply by n, divide by n, so we'll get n I of x1t, x2t, y3t given t. Right? That's clear, right? It's just the average inside here. And now we have to try to get rid of that t, but that turns out to be easy here. Sometimes, for some problems, you can't get rid of that t, so you should always make sure to test. And maybe we have to check that, right? So for the first quantity, we can clearly get rid of the t, right? Here we can clearly say that's less than or equal to h of y3t. Here we should check, can we get rid of the t or not, right? Is this equal to getting rid of the time-sharing random variable? Well, to do that, let's just write out what the joint distribution of these random variables is. If we look at how this was defined, then we have the joint distribution of t, x1t, x2t, y3t is, let me actually just write it like this, t, x1t, x2t, y3t. Well, that's just p of t, p of x1, t, x2t, given t equals t, but, well, it is what it is. I guess I should write, if I write it formally, it would be x1t, x2t, given t. And then here I have p y3t, given x1t, x2t, right? I would have the t there. So what I'd like to do is get rid of this t here, right? But notice that because the channel is time invariant, right? This is just x3, x1, x2. Like the probability of getting y3t at that time given x1t and x2t is just a function of these two plus noise. It's not a function of the time anymore because it's time invariant. So in fact I can drop this, and that's what lets me drop that here, right? Because that is what the joint distribution is, how it's defined, okay? It's because this is time invariant. If it wasn't time invariant, of course, then I'd have to keep the t because then I have an averaging over the channel. And then I would actually have to keep that t here. And that t is sometimes useful to strengthen bounds, in particular, like for the Mac, where if you know the time, the two inputs have to be independent. So then you even want to keep the t sometimes. But here, because we have any joint distribution on x1, x2 anyway, we don't care about keeping the t. So anyway, that was just quickly, to check this, we actually have to check the joint distribution that we used where we define this t and how it's related to these objects. So indeed, this is less than I of x1t, x2t, y3t. And now I just rename the random variables. I'll just call this x1. I'll just call this x2. I'll just call this y3. Okay, that's just a renaming. Where the important thing is that y3 is generated always from x1 and x2, as we saw. It's this py3. py3t given x1t, x2t is just p of y3 given x1, x2. You know, that just follows from how these random variables are defined. So anyway, there's the second bound. There's the second bound. So the first bound, goes the same way, except slightly different choice. So the first choice we'll make is we'll just stuff in y2. That's the main step, right? Which sort of looks reasonable, right? y2, y3. And now we just repeat everything. So this is summation from I equals 1 to n, h of y2i, y3i, y2i minus 1, y3i minus 1, minus h of y2i, y3i given w, y2i minus 1, y3i minus 1. Here, this thing here is greater than or equal to h of y2i, y3i, where we stuff in x1i, x2i, and the rest, but then we can drop them, right? Because they're, there's the Markov chain. Now here's the important point. We need to get x2i into here somehow, right? So how do we get it in? Well, notice that x2i is a function of y2i minus 1. So we can just stuff it in. Right? And then we just drop this, and we're done, right? Because then we're going to get here less than or equal to. And that's also how the general Cutset bound works. All you do is you stuff in some extra information, then you use the fact you can, everything that's on the complementary side, the inputs will be a function of those things on the complementary side, and that's how they appear in the conditioning. And now we just repeat, right? This is n times ix1t, da-da-dum, and then we drop the t, da-da-da-da-da, you know, so then we get the second row here. So that's Cutset, okay? So now if we compute this, so is it clear? Maybe the only thing clear wasn't how the joint distribution happened, right? But that comes from how the t is defined, right? So it's just writing it out formally. Okay, so if we agree with that, the only thing that's left is now to try to see what the Cutset bound looks like here. Clearly, this second term is the same. Well, oh, by the way, Cutset bound for Gaussian channels will always be maximized by Gaussian distributions, because these expressions always will have, when you condition, you always write out the entropy of this minus the entropy of this given that, and then the second term will have always all channel inputs in the conditioning. And so you'll just get a bunch of noises here, and the bunch of noises is a constant, the entropy is a constant. So all of these mutual informations are, the maximization is always an entropy maximization problem for all of them, and usually what happens is that for all of the mutual informations it's the same Gaussian distribution that maximizes the entropy. Well, I should be careful with that. We write it out, maybe I should write it out more carefully. So here I'm going to get hy2, y3 given x2 minus constant. Here I'm getting h of y3 minus constant. So I can always write this is less than or equal to 1/2 log of, here it's 2 pi e squared, covariance matrix of y2, y3. And similarly here, less than or equal to 1/2 log 2 pi e power of variance of y3. So the important point here is that this bound becomes a second order statistic maximization problem. And that, so rather than having to maximize over all distributions, we know the class of distributions that maximizes all of them, right? Because you just use the maximum entropy theorem based on second order statistics to do the bound. And so this maximization simplifies enormously. It becomes a covariance matrix optimization, namely the covariance matrix of the input is what we have to optimize. Okay, so that's common for all Gaussian networks. So the Cutset bound, because the second term is always just the entropy of the noise, which is a constant, will always get Gaussian maximizes the Cutset bound, which is really nice. Also, there's another nice thing about this bound. It's actually a concave programming problem, because every one of these terms is concave in the joint input distribution, which is a convex set. So you have a convex programming problem, and the intersection, the minimum of concave functions is again concave. And the same is true if this min becomes an intersection and this max becomes a union. It's always a convex programming problem. So that's what's nice about the Cutset bound. It has a lot of nice structure. In any case, let's try to analyze it. This just becomes that. So the only thing that's a little tricky is that one. The way I remember it is that it gets a little bit ugly. The final answer that comes out is really simple. But it gets a little bit tricky. Well, we can think about it quickly. So let's look at this here. So the main problem we have is this entropy. Okay. And the trouble with it is here it's like 2 values, so we'll have to worry about covariance matrices, but let's look at it quickly. So y2 is x1 by d plus z2, right? y3 is x1 plus x2 over 1 minus d plus z3, and now we're conditioning on x2. So of course I can get rid of the x2 term, right? That doesn't change the differential entropy, so I'm left with this. I still don't really like to have, well, I guess there's two ways of doing this, either through the big matrix, which I don't want to do, or I'm going to use simplification here, so I think you'll believe me, but so the trouble here is we have correlation between x2 and x1, right? That's the problem with it. So, however, if there is a correlation, we say it's rho, that's what this rho means, then I can always write x1 as rho times, I have to normalize the power though, so root of p1 by root of p2 rho x2 plus some independent noise of appropriate power, right, of x1 tilde, where this is independent of that, right? So for Gaussian random variables you can always do this, right? I can split, if I have two correlated random variables, I can always write one as a linear combination of the one random variable plus another. So let's see if we get the right rho here, right? So if we take here expectation of x1, x2, I would get, multiply this all by x2, I would get the root of p1, root of p2, rho, and then p2, right? So that's fine, because I get root of p1, p2, root of p2 rho. So that's okay. Now let's try to figure out what the power, so the correlation is fine. So let's try to figure out what the power of x1 should be. So the power of this is p1 by p2 rho times p2. So the power of this should be p1 times this times 1 minus rho squared, right? Oh, rho squared. Yeah, so the power of this should be p1 rho 1 minus rho squared, right? So let me just use this in here, because then I can cancel off the x2. That's the nice thing. So this, and I get independence. So this thing here just becomes this over d. So the x2 term plus the x1 term, the x2 one I can subtract out, so I'll just get x1 tilde by d plus z2 and x1 tilde plus z3. Given x2, but x1 tilde is independent of x2, so I just get this. And that's nice. That one's much easier to do, where the power of x1 tilde is p1 1 minus rho squared. Okay, so that's a way of just making things a little easier than going through big matrices. If I was programming this in MATLAB, it wouldn't be so much of a problem to make the whole matrix, and then you take determinants, but it's a little bit harder here. So what do we get? Well, now we have to do the covariance matrix, 1/2 log 2 pi e squared. Those 2 pi e's always disappear, but we need the determinant of the covariance matrix. What is this? This is going to be p1 1 minus rho squared by d squared plus 1. What is the cross correlation coefficient? It's by d, right? So it's going to be p1 1 minus rho squared by d. Same thing here, right? Because it's these two. And the last one is just going to be p1 1 minus rho squared plus 1. Determinant. So we get this whole cross product, and everything should simplify out, hopefully. Let's see what that is. That is the product, right? P1. Anyway, so we get this times this minus this cancels. The first two cancel. So then it's just the remaining terms. So we'll get 1. This changes then to just the remaining terms. For the Cutset bound, this becomes 1 plus this term plus this term. So we do get p1 1 minus rho squared by d squared, but we'll get an additional term, namely plus 1. Right? That's what we got instead. So that becomes the log to 1/2. That's the Cutset bound. And it should make sense because this is just the maximal ratio combining term. We could have done it that way too, I suppose. You know, it's the energy I get from the direct path plus the energy I'm getting to the relay, right? Because I'm going Y2. So this is the energy to the relay. So this is as if I had two receive antennas, one placed at position D and one at 1. And the one placed at position D has this energy, the one at the final is this, and so maximal ratio combining will give me the sum energy. So it's like one transmit antenna, two receive antenna with maximal ratio combining rate. Okay, now if I plot this, so if I now do the, I'll get a different row, of course maximizing this over that, but as mentioned, the curve touches this one, it goes something like this, touches this one, and then and then it looks, if visually, if you plotted this, I think this is for powers of 10, I think, for all this plot. Visually, it's indistinguishable from decode forward, but it turns out it doesn't touch it anywhere except at that one position. Then out here it goes higher and then comes down through here, something like that. That's the Cutset bound. So this white bound is too low. Right. Anyway, something like this. It's just a cartoon, but something like that. Okay, so where we don't know the capacity is anywhere except for that point. But visually it's indistinguishable, which tells you decoding forward is really close in this, for this problem for full duplex single antenna channels. Decode forward is pretty good until a certain distance. And I think I overemphasized this distinction. I think it kind of goes more straight, but let's just leave that as a cartoon. Okay, any questions about that? Okay, if not, let's go to the next strategy, which I definitely want to cover today. It's called the partial decode forward strategy, which should, oh, actually, no. Okay, so we'll do some simple things first. Simple things first. So let's talk first, before we go on, let's go to physically degraded relay channels. This is kind of a little bit more fun than the partial decoding rate, but anyway, physically degraded relay channels. So we've seen that for broadcast channels, when we have a certain degradation, we can prove certain things are optimal. So what I'd like to do here is show a class of channels for which decoding forward is optimal. These are called physically degraded. So the additive white Gaussian noise channel feels degraded, right? If you're thinking of the channel, like what I mean by feels degraded, if we think of broadcast channels, as long as D is between 0 and 1, it kind of feels like the relay has a better channel than the decoder, right? It's closer. What's wrong about this feeling, is if we get it from the broadcast channels, is that, of course, destination is helped by the relay, so its energy is boosted. But okay, but maybe our feeling is okay if it's like, suppose the distance is like 1/10. Suppose we're in a range around the source. Doesn't it feel like the channel should be degraded? What I mean about this feeling is that whatever the destination can decode, shouldn't the relay be able to decode it too? Why? Well, the SNR in free space propagation is 100 times higher now, right, than at the relay than at the destination. So if I have 100 times, and even if I do perfect beamforming, I can only increase the receiver power by a factor of 4, right? So there's still 25 times higher SNR in this range for the relay than for the sync. So shouldn't, whatever coding scheme I choose, shouldn't the relay be able to decode if the destination can decode? If that's the case, then I have an additional cut, because then the relay is also a receiver, right? If the relay is also a receiver, then I have this cut here. And then this is an additional term I can add, namely I of x1, y2 given x3, right? And I would immediately have the capacity, because that's the decode forward rate. So intuitively, I would guess that in a certain range where these two curves look numerically indistinguishable but really are different, I should be able to improve the Cutset bound to go down. But no one's ever been able to prove something like that before. I think it's true, but I don't know how to prove it. Right, that would be a very nice thing if one could prove something like that, because then one would immediately have an improvement on the Cutset bound, which is valid for all kinds of problems. You know, so it would be a very general thing. But I don't know if it's true because I don't have a proof, although it feels right, right, intuitively. Anyway, I won't say more. So, but now so as we already see, this channel isn't really degraded in the sense that this matches that. So let's define a physically degraded channel for which clearly the receiver can decode if the relay can decode if the destination can. So let's suppose that we have the following Markov chain: x1, x2, y2, y3. Right? So if we look at this Markov chain, is a Markov chain. If we have this, you know, clearly this is what the relay knows and definitely knows more than the destination. So suppose this is true. Now this turns out not to be true for our Gaussian channel. Then we have the following. If we look at x1, y2, y3 given x2, namely this term here, clearly it's just going to collapse to the decode forward rate. So it becomes completely obvious that decode forward is optimal now. Right? Because this means exactly that this is 0. Right? So if we have this Markov chain, then the Cutset bound becomes the decode forward rate. So, but as we see here, this is a much more restrictive class of channels than we'd like to study. We'd like to study the Gaussian channel. Okay, so that's called physically degraded relay channels. So the notion of degradation for relay channels is not quite as extensive as for broadcast channels. That's something important to keep in mind. There is no real stochastic degradation. This is purely, because also the capacity will depend on certain marginals here. That's part of the problem. Okay, so is that clear? So let's talk about one other type of degradation that's called reversely degraded. So the reversely degraded channels, we just swap y2 and y3. So a channel is called a relay channel is called reversely degraded. Reversely, I don't know. I don't know how to spell reversely anymore. That doesn't look right. Is it with EY? It's just without this? This? It is there? Look, it looks wrong. I don't know. Maybe it was right. It's terrible. I see I passed my spelling test. This is what we mean by reversely degraded. Okay, so a lot of these things are just sort of made up a little bit to make things happen, right? So now I can just do the y3 first and do the y2 second, right? So that's 0 now. Now, okay, so this first bound here is just ix1, y2, y3 given x2. So let's look at that. Now this is tighter. If we had that here, y3 given x2, clearly that's less than this. So that'll be the dominating bound. But this is easy to achieve. How? This is an average mutual information, right? And the average is always less than the maximum. So let's just choose the maximum. Max over all inputs of the relay. And this I can clearly achieve by just having the relay always transmit this one letter, usually 0 if you think about Gaussian channel or something like that. You're just choosing the best channel from the relay, and now you're just sending a point-to-point. You just have a point-to-point channel. So that's easy to achieve. So the capacity of a reversely degraded relay channel is also given by the Cutset bound. And it's just achieved by point-to-point communications. I mean, we're sort of just playing around with channel models and trying to find when is the Cutset bound optimal. Okay? But these insights are actually useful when you're playing around with the information rates for some of the more sophisticated strategies. If I get to the noisy network coding, I can say a few words about it. This sort of situation appears there, in fact. This mutual information, not reversal degradation, but that term appears. Okay, So let's go to partial decode forward. So I would like to complete that today, and then we can do quantize forward tomorrow. Quantize forward takes a little bit of work, so it's a little bit more sophisticated to do the information theory, even though the idea is very simple, but the information theory is a little bit more intricate. Okay, so for partial decoding forward, we're trying to use, we're trying to avoid the relay having to decode everything, which we've seen is not necessarily good. Okay, so how are we going to do this? Well, what this method involves is a mixing decoding forward with direct transmission. Because fundamentally all we want to do is have the following. We'll let the relay decode something, and then on top of that we'll plant just something for direct transmission. That's all it is. So we're doing base level is just decode forward, but we'll change the x1 to be an auxiliary variable, and then to give us freedom to use x1 to transmit some extra information. Right? So if you're thinking of what we're going to do is we're just going to take x1, split it into two pieces, treat one piece as if it was x1, do decode forward, and then send some information directly by superposing on top. So that's the way it works. So let me just draw the block structure. So we'll choose a joint distribution P U x1 x2. So the U and x2 will serve like our decode forward scheme, and then the x1 will superpose something more. So let me first draw the basic levels. We'll do it again for four blocks, and we'll argue somewhat intuitively now. So then I'll put another layer on top in a moment. That will be my superposition. This is block. We'll again use block Markov superposition coding. So same idea, b equals 1, b equals 2, b equals 3, b equals 4. Base layer as before, x2. I'll not write the blocks. Maybe we'll do it by backward decoding. We can do either sliding window coding, backward decoding. Here we'll have 1. Here we'll have, we'll have to use rate splitting. Use rate splitting. So it's like multipath routing, right? So W1 is split into W1 primed with rate R primed, and W2 1 double at 1. I don't need 1. B double primed with rate R primed, and this has rate R double primed. Right. So it's like doing the multipath routing. So here we'll get W1 primed, X2N, W2 primed, X2N, W3 primed. We do superposition coding in the usual way. We'll start with PX2, then we'll do PU given X2, and then we'll use PX1 given UX2. So we're doing superposition coding over 3. We'll stack 2 code books on top. Here we'll do the U's. U, UN, we'll want this as a base layer and add W1. Here we'll send our first block of messages, W1 primed, and so this will just operate like decode forward. W1 primed, W2 primed, right? So we're just bubbling through, right, the block Markov, crouch UN, W2 primed, W3 primed, UN, W3 primed, and now a default index, so we lose one block, of course. And now on top of all this, we will superpose xn, so x1n, with both of these 1, W1 primed, W1 double primed, x1n, W, so these are always like sub-blocks. W2 double primed, these are the new ones. 2 primed, and here x1n w3 primed 1, 1. We could also add another one there, but so here we could even in fact send another message direct if we wanted, but I'll not worry about that. Okay, is it clear what we're doing? Right, so this is the stuff that goes directly. Okay, and now if I was going to, I can do this with sliding window decoding, and then I'd have to, formally for the proof, I would have to choose a new independent code book in every block. Or I can do it by backward decoding. Let's do backward decoding. That way I won't have to worry about this. So the relay has to do forward decoding. So here I'll do the relay, I guess, next. I should have done the relay first. But let's start with the destination, Gesundheit. Suppose I do a joint decode. Suppose I just look at the last block and I decode W3 primed. I guess maybe, well, if I decode W3 primed jointly, I'll get something. But now let's look at the next block. So I have no W3 primed, but now I have to decode Maybe what I should do, maybe I should shift that, here in this. But you get the problem is I want to also decode, here I have to decode two things, right? I know W3 primed, but I have to code W3 double primed, right? And W2 primed. So let me look at this block, assuming that I've gotten W3 primed correctly, right? So the ones I've decoded, that'll be the more restrictive case. Or I could have shifted all these W's by one, then I would have seen it more clearly. But so in this block, these are the ones from the previous block that I've decoded already. Those two. And now I have to decode the other pair of messages, right? And this will be more restrictive than the first case, because in the first case I actually know this, right? So let's just do it this way. So what rate do I get? Well, I have two messages to decode, which means I'll get 3 error rates, 3 error events again, right? So I have to worry about 3 error events. Let's do them in the order. So I'll have W2 prime not equal to W2, and W3 double primed equals W3. What do I have there? What kind of rates will I get? Well, I'll get R primed. Should be less than, let's see, what is the situation? So I know this one here is correct, but all the others are wrong, so I get all 3 of them are incorrect, right? So we'll get x1, x2, u, y3. And of course this is equal to I of x1, x2. Because all 3 of them for an incorrect code word, the probability that a random choice is wrong is that, all 3 will together be wrong because they all carry the same index. In fact, I may as well, if I do the case where both are wrong, I'll get a tighter bound, which will just be R prime plus R double primed, so R less than that, right? That's the double case. So the one case that's left is that W2 primed is correct and only this one's wrong. Aha! Now these two are jointly typical, only this one isn't, and we have that funny situation where we have the case where we have the following experiment U, x2, y3. y3n is typical, and here I'm getting u2n is typical, and x2n, un is typical, and x2n are typical, and these two jointly choose the x1n. So here I'll get R, and this rate is double prime, has to be less than I of x1, y3 given u, x2. Right? So those are the 2 bounds I get out of my... Okay, I know it went a bit quickly, but I'm just using always the same steps. I'm just going fast through them, and after you get used to this, you sort of know what things to watch out for. Okay, so that's the 2 bounds at the destination. And now, once we've done this, we go back, do here, go back, do here, and decoded everything, right? And the first one is even easier because I don't have to worry about this last error event. So, anyway, the other ones will be limiting. So let's do the relay. Let's do the relay decoding. So what does the relay have to do? Well, the relay has to decode, after block B, has to code W1 primed. what rate do I get there? Well, I of u y2 given x2, right? So we get the bound r primed less than I of u y2 given x2. And that's it, because now at the next block we just have the same situation, and so on. So there's our three, I have three bounds. Now I just add these two up, right? Fourier-Motzkin elimination will just add these two. So I get two bounds on the partial decode forward rate. So let's look at this RPDF, which in general, this generalizes decode forward, right? Because decode forward is a special case of this. So RPDF is going to be equal to the max over all three u x1, x2 of the min of two rates I u y2 given x2 plus I of x1, that's the direct transmission, 3 u x2, and I of x1, x2, y3. Right, so, and the interesting thing is this lets us do multipath routing, right? So let's take a look at our little network that we have. x1, 1, y2, x2, y3, 1, y3, 2, x1, 2. Capacity is 1. What will we choose? Well, we'll choose u to be y11, x11, obviously. And if it's noise-free, we would get y2. Just suppose it's noise-free. And that's it, right? And then we would choose u x12, x2 independent. And then this term will get 1. This will be 1 because that's the direct path. So this will be 1 plus 1 gets 2, and this will be 2. So we get 2. And it just corresponds to the fact that now we're permitting this guy to decode only part of the message, namely, because we have a vector channel, we can just load u onto this path. So partial decoding forward includes multipath routing in networks. The u is just the second path. If we wanted to be very explicit about it, we could have just said, well, let's just choose x1 to be something like, u plus v or something. Well, for wireless channels we can do this. I can't do it here, not for this network. Anyway, but you get the idea, right? So this is just a way of including routing into the information theory. That's what's happened here. Okay, questions? We could do this now for the Gaussian channel, so I could define, usually what you do is you choose this to be jointly Gaussian. You choose this to be jointly Gaussian. You optimize over all correlation coefficients, you apply it to the full duplex Gaussian channel, and you find that you don't get any rate gain, unfortunately.
You can keep on stacking like that as much as you want.
Yes, but why would you if you only have if you only have one relay? So yes, so if you had, we'll talk about that. So if we had two relay nodes, then it's natural to start stacking more. So that we'll define a decode forward scheme with stacking, which doesn't have auxiliaries. And for those problems, you could then again add auxiliaries to those if you wanted to, because then you have many paths. Like networks become more complicated. But yeah, you could. But you can't forget, the more you do this, the more complexity you're building into your whole system. So there's, you'll have a combinatorial explosion of the number of possibilities. And the problem with that is you don't get a lot of insight from that, right? So if you have a large network, you're going to have to do something simpler. But that's why we're focusing on small networks. It's because we're trying to develop what is possible in principle, right? And methods that we can build for little networks, like point-to-point channels, two-way channels, relay channels.
Suppose there are 2 points and there are 2 relays.
Yeah.
So how would this problem get modified?
Well, let's wait and see for tomorrow, because then I'll talk about two methods for networks. One is this, generalized multi-hopping with decode forward, and a noisy network coding, which extends the quantized forward scheme. So I think I should at least be able to outline that. So there are ways of generalizing these methods, and a lot of the work since around 2005 has been on extending basic strategies to larger networks. In fact, there's even some very recent results. They've just been published a few months ago on extending, like connecting Martin coding together with this kind of decode forward method, which is nice. So nice rate expressions, awful implementation, terribly complex implementation, but the final rate expressions look really nice, the information theory expression. But I just wanted to point out, first of all, for additive white Gaussian noise channels, full duplex. It turns out, surprisingly, I think it's a little bit surprising, you don't get any improvement for the full duplex case by using partial decode forward. So for the full duplex additive white Gaussian noise relay channel, you may as well have the relay decode everything. So you won't, if you do this numerically optimize, you'll find you'll get exactly the orange curve. If you do half duplex, then you do get gains. And that should be clear, right? Because with half duplex, the relay has to listen sometimes and sometimes transmit. And since it's listening only part of the time, it should only try to decode part of the information. Because when it transmits, the transmitter can pump information through directly, right? So there, for half duplex channels, there it helps to have partial decoding forward. But for full duplex, it doesn't. Let's do one other example. So there's one other example where it's very closely related to this, where it's known that this method is optimal, and that has to do with having certain deterministic links in your channel. So I'll do that one. That's an important example to understand, I think. It's called semi-deterministic relay channels. And it fits also a very practical situation, so semi-deterministic. What we mean by that is that effectively, if you think of node 1, 2, and 3, we basically, the way you can think of this is this is just a wire, okay? And it's noise free. So what we mean by semi-deterministic is that y2 is some function of the two inputs. And usually we're just interested in one of the inputs, but let's just say it's more generally it's a function of both of the inputs. So this would fit a situation where here we have a remote antenna, we have our own local antenna, and we're controlling a remote antenna via a wire, and then this here is a MAC, for example. Right? So you can have it's natural to have such a practical situation. I just have another remote antenna which is connected by some finite capacity link. Then we would have a situation like that. So it turns out partial decoding forward is optimal for such problems. And the way to prove, which is natural, I think you're sending part of the information to the other antenna, right? And to do that, what we'll do is just choose U to be we're choosing U to be Y2. So we'll choose. Okay, so the first question is, are we allowed to do that? Well, remember the Markov chain that we have to have here is the following: U, X1, X2, Y2, Y3. So can we choose U to be Y2? It seems like we're breaking the Markov chain, but the answer is no, because Y2 is a function of X1, X2. And because of that, I can also make U Y2. Right? That's why, because of the functional relation. Functional relations always have, if Y is a function of X, then this forms a Markov chain, even though it looks like we're breaking it, but it's because of the functional relation. You have statistical independence. So I'm allowed to choose this, which even makes sense, because since this guy knows what the output is through the function, and this guy, with partial decode forward, the source is controlling X2, and since it controls X1, it's controlling both. So anyway, we choose U to be this, and then just plug it in. What do we get? R equals max P of U X1, X2. No, we're choosing, well, we're maxing over now P of X1, X2. Of course, P X1, X2, because now we've chosen U to be Y2. Well, if I have here I y2 given x2, that's just going to be the entropy. Plus I x1 y3 given x2 y2. Okay, but this thing here I'm claiming is equal to I of x1 y2 given x2, right? Because this is just the entropy of y2 given x2 minus the entropy of y2 given x1 and x2, which is 0. And now I add these two up and I get the Cutset bound. So this is actually the capacity. Our PDF is then the capacity for those problems. So that's why, so Abbas wrote a lot of papers like this, like some examples showing when something is optimal, right? So this is one of them. It's a short paper, maybe 2 or 3 pages, that's about it. But it develops this partial decode forward scheme also. That's, I think, more important from that perspective. Okay, so that's an important point. Right, so that brings us to quantize forward, which is too late to start now. So what we'll do tomorrow is develop a coding scheme that does what I suggested, right? So if the relay is here, what we should be doing is having the relay not decoding anything. And what can it still do? Well, it sees like sampled values of the waveform, right? And what it can do all by itself is always just quantize those values to bits, then re-encode those bits and send those on. And here it basically can pass its entire waveform to the destination. And if the destination has both, then has 2 waveforms available, 2 looks with independent noise, and it's the same thing, and then it would do maximal ratio combining, and so it's the 1 transmit antenna, 2 receive antenna case. This is more important if, suppose the source has 2 antennas, then we would get 2 by 2 MIMO this way. So then the rate boosts are very large. Since here we're looking only at the scalar case, the rate boost is only is only a power gain. But if the transmitter was a 2 antenna system and both the relay had 1 antenna and the destination has 1 antenna, so 2 mobile stations, now it makes sense. So if both of you have your mobiles with 1 antenna each, you're near each other and you want to help each other, one mobile could quantize its rates, send it off to the friend, and then you could actually, the receiving person now has both waveforms, and now you even get a degree of freedom boost. Right? So you can boost rates a lot that way. That's where the bigger gains will come if you have a 2 by 1 by 1 style system. Okay, but here we're just looking at 1 by 1 by 1. The compress forward scheme turns out, remarkably enough, also to be optimal here. So we'll talk about that. It actually also gets to capacity here. I can't remember where it goes here, whether it goes above or below decode forward. I think it's still going to be below for a while. It doesn't go as high, but then it stays more robust in some sense, and then it comes down here on the Cutset bound. So what happens is that this quantize forward, so this is decode forward or partial decode forward. This will turn out to be the quantize forward or the compress forward. I'll explain where the names came from and what their differences are. So which one would you choose, decode forward or quantize forward? Well, it depends on the geometry, right? It depends. And then I mentioned multi-hop here. I have to try to remember what the performance looks like. But I know it starts here. I think maybe it still does go up. I'm not sure. But there are cases where it doesn't even do better than without a relay. But I forget now. Maybe it looks something like this, or maybe it looks something like this. But it's much, much worse, the classic multi-hop. So doing this, the most important thing is not to lose a degree of freedom so that you're always transmitting something. But also the beamforming helps as well. Okay, so you'll find these curves in the course notes anyway. So there you'll see the exact computations for these problems. So there's a couple of interesting things. First, The MIMO case is interesting to maybe redo the plots for, then you'll see the larger boosts in rate, especially here. This rate will pop up to here now, suddenly, right? And in high SNR, that's really important, that gain. And the second thing to look at would be half duplex channels, like, because a lot of these things are half duplex. So you'll still see the boosts for those problems. Okay, any questions? Okay, so tomorrow morning I'll again review quickly what we did today, then we'll cover the quantized forward scheme in one of the hours, or maybe 1.5, and we'll finish in one of the hours, and then we'll maybe finish with very quickly some statements about decode forward for larger networks, and also the noisy network coding, which is a natural generalization of it's just quantized forward in larger networks. The hard part is computing the rate regions, but we'll do that too. Okay, thanks.